Hey, Lyle.
Hey, Dr. Wheeler.
Let's see, I gotta pull up my notes here. Try to remember what we got to last time. I think we finished one of those calculations. We're going to move on to the next one.
I think, I could be wrong about this, but I feel like we started talking about the Feynman rules, or we're getting close to talking about them.
Yeah, that's right. Possibly one more example. You know, what I really want to do is enough examples that extracting the Feynman rules is an obvious set of things. Let's see. So probably April 16th is the latest version. All right, here we go. Yeah, that's what I was thinking too, is that we were right close to the rules.
I guess I'm the only one coming today.
No, here comes Guillermo. Hey, Guillermo. And here comes Kevin. Yeah. Yeah, we'll get a quorum here. Now let's see. So we did first order scattering matrix. Yeah, I think. Did we do a second order case? Anybody remember the last example we did? You've got it there, Kevin, don't you?
Yeah, I mean, we there were 3 that we addressed, and then we worked one of them. And
it was the 2 particles, so a cubic reaction at second order. I think I'm remembering. So no, somebody hasn't erased the board. Yeah, I think I remember, and I left the other 2 as exercises. So, guys, do the exercises. Have you worked any out?
In the process of?
Yeah.
Yeah,
Same.
yeah, good. Okay. Yeah. That's the marker. So yeah, I did this diagram, and there are 2 more where it's this is a time-like channel, this is a space-like channel. There are, eventually I guess we'll get to Mandelstam variables that are ways of formalizing some of that. But yeah, so I did this one. Then there's a third one where these 2 come out the other way. So this one scatters there, this one scatters here. So those are the 3 simply connected diagrams. And then
that last one is also considered space-like, yeah.
Yeah, these 2 are space-like. All you have to do, once you've done one of them, you can just interchange a couple of the momenta, and you'll have the other one. So you don't actually have to work it all out again. But, you know, then there are some further diagrams that are connected. So you could have the particles go non-interacting and put your 2 interactions here. So at one of these points, you're basically creating 3 particles, and they all annihilate over here. That's That's a legal diagram, but it's a little bit pathological. Hey, Eli, Alex, how's it going? Or you could have one that does it this way. Similarly pathological, but different. And you could have this time-like or space-like. But these are some possible things. So let's see. Okay, I worked through this. I want to do a quartic interaction at second order, and I'm just going to do one of the one of a couple of it's very similar to the case we just did, but it introduces a new feature. So with a quartic interaction, you can have the two particles, and remember the problems we're doing so far, we're always talking about two particles in and two particles out. Doesn't have to be that, right? We could have 2 in, 1 out, 2 in, 3 out. Any of those are possible, but if we have a quartic interaction here, then these guys can come back together and have another quartic interaction there. And that can also be space-like. So we have a diagram like this. So these 2 in, those 2 out. And we can interchange these 2. So we have, let's see, something like this, but then from here, I don't know, it goes this way and that way or something. There's probably a better way to draw that one, but it's just this one with the final momenta interchange. So let's work out this first diagram. And the thing that's novel about this case, I'm going to draw this a little smaller.
Sorry, Professor.
Yes.
You're counting the order of the interaction, right, by the number of vertices or the number of edges at every vertice.
It's the number of vertices. Now, okay, I'm also varying the type of interaction. So we've done one quartic interaction and one cubic interaction. So this case is quartic, where we have like this. So at each vertex, there are 4 lines coming in. So that's a quartic interaction. We're doing it at second order because we have 2 vertices. Okay, so now we have, well, the integral part. There are the things that'll cancel and some coefficients, but the basic integral that we need to compute. Let's see. I'd better label things here. So let's have x1 and x2 in, x3 and x4 out, and I think I can get away with x5 and x6. Did I do that here? No. Yeah, maybe it's, now, let me go ahead and call this y1 and y2. Trying to see, did I label? I didn't label the diagram. Okay, so let's just call this y2 and y1. So we're going to have propagators, 1, 2, 3, 4, 5, 6 propagators. And here comes Tyler. Hey. I think we got everybody here today, right? Good. Oh, and while I've got everybody, how many of you want to do this over the summer? Want to continue?
I'd be intrigued.
You know, there is a, what is this, 6330 or 6930. There is a 6940. I don't know if it's on the books for this semester, but we can sign up as an independent study and, you know, give credit for it later, or you can sign up for 6940 later. But yeah, credit wise, that's probably the best thing to do. Quantum field theory too. But let's see, if enough of you are willing to commit to coming to this over the summer, I'll just continue. You know, we may have a break in there. Let's say Meg and I are going to take a trip sometime over the summer. We haven't planned when, so there would be a break for that sort of thing. But and if you like, we can schedule it, you know, a longer period or whatever. We can choose whatever time works for everybody. Let's see, I'm not seeing you on Cam, Eli, or Tyler. Were you yes or no on this?
Yes,
I think I'd be all right with it.
I'm a yes.
Yeah, I can do
Okay,
it.
a couple yeses, and let me see the hands again. And yeah, Lyle, you weren't sure, but
Yeah.
Kevin, how about it? You?
Yeah, I'm not sure. I'd like to talk to Dr. Torre and find out. how
Oh,
much
for
research
sure.
somebody's
Yeah,
done.
yeah. No, I'm not trying to twist anybody's arm, but you know, we've got at least 4 of you who are definite yes. So we'll do it. And yeah, I'm not sure what to sign up for when, but you know, we can sort that out. But we'll definitely slate regular meetings. You know, for some problems, it might be nice to have like 1 3-hour meeting instead of 3 1-hour meetings. You've seen that some of these take a while, and you know, computing a full cross section, you know, you could easily spend a whole afternoon on that. So let's be flexible, but plan on continuing. Okay, so let's try to write down. Yeah, I'll do recordings, Alex, for sure. Okay, so yeah, and yeah, figure out how to make those accessible to everybody, even if you don't come to all the course, you could watch the recordings. Okay, so we're going to want to integrate over all 4 d4 x1, d4 x2, d4 x3, d4 x4, and over the y's. That's y1, y2. Okay, and then we integrate over each of the propagators. So we're going to have d4 q1, you know, let's just say d4 q6, because we have 6 propagators. There's 1 for each line in the diagram. And then we have the exponential in all of the external fields. So e to the I, and I think I've got these positive. Yeah. P1 dot x3, P2 dot x4 minus K1 dot x1 minus K2 dot x2, like that. And then we have the propagators. So let me see, 1, 2, 3, 4, 5. Yeah, there's 6. So we're going to have 2 pi to the 4th 6 times is like 24th, right? Let me just pull that out. And then it's all the q's. Yeah. Yeah, we have the product over all of the q's, qi squared minus m squared. So I'll not write all of that out quite yet. And then the exponentials for the different propagators. And now that I've been choosing, yeah, minus in the future one. Okay, so minus I q1, then we've got an x3 minus y2, e minus I q2. Doesn't matter what I call these q, which q goes with which. All the q's are symmetrical now, but here x4 minus y2. And yeah, what's crucial here is which y each x is connecting to. And then we're going to have e to the minus I q3 dot, okay, we're going to have a y1 minus x1 and e to the minus I q4 y1 minus x2, and then two more. There are two that connect the y's, and yeah, I just write them that way. E to the minus I q5 dot y2 minus y1. And we actually get that twice with the q6, y2 minus y1. So then we're going to get a whole bunch of Dirac delta functions. So how many can we do? Let's do x1 through x4. So then that leaves us with the, well, let me withhold judgment on the y's. I think we can probably do the y's as well. In which case, 1, 2, 3, 4, 5, 6, we're going to get 2 pi to the 24th, and all the 2 pi's will go away. All right. So if each of these spatial integrals gives us 2 pi times the Dirac delta function, then the 2 pi factors all cancel out. So let's just look at deltas. So taking them one at a time, x1, we've got a minus k1 up here, and then in one of the propagators here, we've got plus q3. And del 4 on x2, we have minus k2, and x2 is the last one over there, plus q4. Then x3 here, we have del 4 at minus q1, and what I forget up here, x3 plus p1. And del 4 at p2, and here, right, minus q2. Now, let's see, for the y's, let's see, I guess we can do the y's. They're all going to occur here, and they're, each one occurs several times. So let's be careful here. We have a plus q1, right? Wait, no, let me do y1 first, just so I don't get lost. So minus q3, minus q4, plus q5, plus q6. And then for the y2, we're going to have del 4 at q1, y2 plus q2, minus q5, minus q6. Okay, and the 2 pi's canceled. And then we have a product of qi squared minus m squared. We're going to have to break these out of this next step. So, all right. So these four all just replace a q with either a p or a k. So we're going to get, and those terms are going to cancel the rest. I didn't write the whole matrix element here, but these are the four that are going to cancel. So we're going to have p1 squared minus m squared, p2 squared minus m squared, k1 squared minus m squared, and k2 squared minus m squared. Okay, so that's each of these, and that's doing the integrals over q3, 4, 1, and 2. So we have two more integrals over q to do. Is everybody with me? You're okay. So I'm almost automatically implementing the rules here. It's you know, it's fairly straightforward what happens. Now q5 and q6, I need to be a little careful. I'm going to leave d4 q6 because when I integrate over 5, it's going to stick a q6 into this thing, and I want to keep track of that. So q5 is going to be equal to q3 plus q4 minus q6 from this delta function. So we're going to have a delta of q1 plus q2 minus q5. So I need minus all of this, minus q3 minus q4 plus q6 minus q6. Okay, you see what I skipped here, right? Q1 through Q4 have actually turned into P's. And this is giving us conservation of momentum. Huh. Is this right? I feel I'm missing something. Oh, yeah, the denominators. All right, got to keep track of the denominators. So, all right, so Q1 became P1. Q2 became P2. Q3 became K1. And Q4 became K2. And those two cancel. So we have our conservation of momentum here. That's good. Then we still have some denominators floating around. Let me put them here. We're going to have, what was it? So we're going to have Q6 squared minus M squared, because we haven't done the Q6 yet. The Q5 squared, Q5 became all of this, which is, let's see, we need Q3 and Q4. So that's these two. So K1 and K2. K1 plus K2 minus Q6 squared minus M squared in the denominator. Okay, I think that's looking right. So when we put this all back into the matrix element P1, P2, time ordered product of stuff, or no, this is what we've called IT. K1, K2. Okay, so when we compute all of that, there are 6 propagators. So let me get the coefficient here. Let's see. This is quadratic order. So we're going to have a minus I lambda cubed. The 3 factorial goes out for each one of those. Sorry, squared. Each of those was over 3 factorial, but there are or over 4 factorial, I'm sorry. Each was over 4 factorial, but that's how many different ways you can link to the 4 fields that occur at this point. Then there's an overall z squared. And at quadratic order, you have a 1 over 2 factorial. Remember, we're expanding an exponential. Then I'm going to multiply and divide by 2 pi. So I'm going to put a 2 pi to the 4th here and a 2 pi to the 4th with the delta function. So we have our usual factor, 2 pi to the 4th times conservation of momentum. Like that. And then these guys all cancel with the same factors in the numerator. And I'm thinking we've got everything except the last integral, which I'm going to call, let me call it I sub q at k1 plus k2. Because k1 plus k2 is what occurs here. Instead of q6, we pulled out this delta function. That's out of this integral. So this last integral, IQ, is the integral d for, I'll drop the subscript. We have a 2 pi to the 4th.
We got a board check.
Oh, sorry, thank you. Okay, so conservation of momentum, the usual stuff we expect, and there's one integral left, which is, I'm calling d4q, it's q6, but I'm dropping the subscript. And then we have 1 over q squared minus m squared times k1 plus k2 minus q squared, k1 plus k2 minus q, quantity squared. Yeah, I need more parentheses here. Minus m squared. There we go, like that. So, and this is k1 plus k2 as the argument here. In general, we could evaluate this with just some momentum here in place of k1 plus k2. So now we need to digress to study that integral. Let's see, I worked out diagram 2 as well. Diagram 2, it's in the notes. I won't write it all out. But what happens is you get the same thing, but you get a P1 minus K1 here, right? And remember, diagram 2 looks like this. And if we have P1 and K1 here, then the argument of this integral is, P1 minus K1 is the net momentum happening at this point, and that's what gets carried this way. In this one, it's K1 and K2 are adding at that point, so we have a total K1 plus K2 entering this channel, right? And you can look at these diagrams and pretty much, read some of this kind of thing off. For the third integral, is this one with P2 and P1. So the things that we're going to be looking at, we'll always get an integral of this form, but it'll depend on some momentum where P is going to be either K1 plus K2 or P1 minus K1 or P2 minus K1. It could be any of those, but it's some momentum, and we have D4Q over Q squared minus M squared, and then P plus Q minus M, quantity squared minus M squared. Okay, with a 2 pi to the 4th somewhere. The same thing I've written down here, only I wrote it smaller and sloppier. Yeah, okay, so any questions at this point before we venture into figuring out that integral? You're all looking very serious. Okay,
So I guess I got one. So the the term there, it's like the momentum is being carried along the, like at the vertex, we have some momentum that needs to be conserved there. And so that's what's being pulled along. And that's what we
Momentum is conserved at every vertex. And if you look where we've written the propagators, all right, say everything with a y2. Well, y2 also has an x3 and an x4, and it's got the momentum along these two coming in. The delta function you get here is going to preserve momentum at that vertex. This is going to be one of our Feynman rules for these fields. So we always get this overall conservation of momentum. And we'll see that momentum is conserved at every vertex. So those are two of the features you want to watch for here. Other questions? No. Okay. Yeah, this integral's not nice. So we'll deal with it. Okay to erase the board. Everybody all right there? Okay, here we go. So there's the first trick in dealing with this integral. I guess I've got it down here, so I can erase this. Then a lot of similar stuff happens regardless of what that momentum actually is. So integration variable q, but there's some momentum in all of this. 2 pi to the 4th integral d4q over q squared minus m squared, and then p plus q squared minus m squared. All right, so let me just remember the order of presentation here. I think the thing we first have to look at is what happens when q is large. You know, that's where we run into the tricky bit. You know, what we're doing in this diagram, we've got an internal loop in this diagram, and we're basically integrating over all possible momenta in that loop. So for example, where we have this diagram, right, we're going to match P1 minus K1 plus Q. Q is what goes this way. Well, that Q can be anything because whatever that Q is going to flow out over here. We've got another delta function that preserves momentum there. So we can have a large momentum transfer from K1 to P2. Right? That sort of thing can happen. Arbitrarily large amounts of Q can flow around that loop. So what happens is that in order to see what we're doing, all right, Q squared, it's hard to make Q squared large because we're in space-time here. So Q squared looks like E squared minus P squared. Well, E can be as big as you like. But to study the properties of this, what we're going to do is a Wick rotation. So if Q were large, well, we've seen that energies can easily outstrip masses. If P is fixed, then at the high end, Q squared would dominate this. We'd be integrating D4 over Q squared squared. We're in 4 dimensions. We have to think about how to do that. But to make it easier, we're going to do a Wick rotation. So if we let the time component be extended to the complex plane. So a real plus imaginary part. Now we're allowed to do this if you remember your contour integration, you can just deform contours any way you like as long as you don't cross over any poles. So we'll be careful not to cross over any poles. The first thing I want to do is to displace the poles. So, you know, if we think of this as basically d4q over q to the fourth, when q becomes really large, or the magnitude of q becomes really large, then the poles are going to be at wait a minute. Where are the poles? Yeah, I want to shift them. What have I written here? Yeah, minus I epsilon. So I want to shift q naught. Yeah. So where's the pole? All right. If we look here, q squared minus m squared. What is that? That's q0 squared minus p squared. Minus the free momentum squared minus m squared. So the poles are when q is plus or minus p squared plus m squared. And I'm going to displace those by that amount. And let's see, what I want to do is I want to displace the negative one upward. So if I've got a pole on the negative real axis, I want to add I epsilon to it so that the pole is up here. And the opposite pole is going to now be displaced by minus I epsilon. So we're just shifting them off the real axis. And now the integral we're interested in is all along the real axis. So I've gotten the poles off the real axis, and I can deform this by rotating counterclockwise. I can't rotate the other way because I would cross some poles, but what I can do is deform so that Q0 basically goes to a pure imaginary part. And what that does is it makes the full Q squared Euclidean. So this rotation, called a Wick rotation, makes Q squared equal to minus Q imaginary squared plus B squared plus M squared. So it's now positive definite. And it has to be this counterclockwise rotation for that displacement of the poles. Okay, now if we look at the Euclidean integral, this is now Euclidean. And we want to ask what happens to that integral for large Q. So the next thing that rears its ugly head is four-dimensional geometry. Any of you ever played with that? Four-dimensional Euclidean space, Alex?
Yeah.
Yeah, a little bit. Yeah, so what we need is the, I want to write this in angular coordinates. So I want to write a magnitude Q times three-dimensional angle. We can easily see there's going to be a Q cubed here. Now, working out that angle, I actually want to work through that angle because I'm going to want the coefficient. But notice what happens here. We end up with dq, q cubed over q to the fourth is going to be dq over q. So this goes like a logarithm of q, and that diverges logarithmically. So this is like an ugly fact of life in Feynman perturbation theory. The this turns out to be right. I looked to see whether there might be a divergence somewhere else, like at 0, you know, it looked like, oh, you know, is that behaving in the same way at 0? But no, this thing is nicely bounded everywhere else. You can do all the rest of the integral up to some cutoff lambda. And what you'd like to do in the end is to write expressions that don't depend on lambda, and then you can take lambda to infinity. Perfectly legit. Keeping track of lambda means, okay, we're going to have some terms that go like log lambda. There are some other types of divergence here too, and we'll find that we can absorb those in certain unseen places. Let's see, shall we do a little 4-dimensional geometry? If we write, let's see, you got the Wick rotation. I'm really good here. All right, if you recall 3 dimensions, again, this is in the notes. I don't feel I have to work this all out, but I can write a general vector as a magnitude times n in 3 dimensions, where this is I hat, we need sine theta cos phi plus j hat sine theta sine phi plus k hat cosine theta. And then if I take dr, you know, I have dr times n hat plus r, and then just take the differential, you know, d theta and d phi stuff here. I hat, j hat, k hat are constant. And then if I take the n hat dotted with itself, that's going to be d theta squared plus sine squared theta d phi squared, because we all know that's what it has to be. But if you take the differential and do this, that'll work. Then, and then dr squared is just going to be, you know, if I call this d2 omega, I'm just going to get dr squared plus r squared d omega squared, the usual spherical line element. Okay, so just a refresher of what we do in 3 dimensions. Now I'm going to introduce a new unit vector, which is this n hat, this 3-dimensional n hat, times the sine of chi plus some new direction m hat times the cosine of chi. So I add a new circle, right? And as we change chi, we get more or less of this n hat and less or more of little m hat. And then we do all the same thing. And I'm not going to write out, well, so basically we let this be some big R times m plus, hang on. Yeah, well, and yeah, so, and then putting this in, folds in this n, but now this R is the total magnitude. And you do the same thing. You take dr, and you look at dr dot dr. And what you find is that the 4-dimensional, oh, oops, we need the volume element. Okay, so one more step that you guys all remember from relativity, right, is once I've got, well, this line element, I can read off the metric as 1 and r squared d theta and r squared sine squared theta times d phi. So that's the metric. The volume element is the square root of the determinant of that metric, which in this case is r squared sine theta. And that multiplies the r, d theta, d phi, just the differentials of the 3 angles. Now, so now we do the same thing in 4 dimensions. So we take d of this, we get some long expression with a bunch of sines and cosines, but you just work it out. Then you take dr dot dr, And that's the line element in 4 dimensions. And now you read off the metric, it's diagonal, it's got some extra sines and cosines in it. And you take the square root of that. And what you find is that d4x here is going to be, where is it? R cubed times, what you get is another, you get higher powers of the sine. So you get a sine squared chi sine theta d chi d theta d phi. And I think that's, yeah, that's it. Now, so it's a straightforward procedure. There's a, Wikipedia's got n dimensions written out there. You can look at that and figure out how they do that in perhaps more clever ways, but this is a straightforward way to do it. Now, the other thing to know is that you're adding powers of sine of the new angle here. And the range of the new angle is like theta. It runs 0 to pi. Phi is the only one that runs 0 to 2 pi. All the others run from 0 to pi. And that lets us just integrate this to find the, well, the volume of a sphere in 4 dimensions, a 3 sphere. So if I integrate over the angles, d3 omega, I'm integrating 0 to pi times sine squared chi d chi, 0 to pi sine theta d theta, and 0 to 2 pi d phi. And let's see, what is that? So let's see. Well, we get 2 pi from the phi. This is just d of cos theta from -1 to 1. You get a factor of 2 there. Then to integrate sine squared theta, I always write it as a half of sine squared, or sine squared chi, plus 1 minus cosine squared of chi, d chi. Then I use the double angle formula to write this as 1 minus cosine of 2 chi, 0 to pi, d chi. And I can just directly integrate that. I get pi, so I get pi over 2. And then cosine is going to give me sine of 2x over 2. That's going to vanish at both ends, so I'm done. So I get pi over 2 from that integral, and the result is 2 pi squared for the total angular area of a 3 sphere. Okay, fun, cool, neat, it works, right? You can do this. I did that quickly. Do you have questions? Yeah.
So my question about generalizing this to the other dimensions, are we always
Yeah.
basically restricting our attention to 3 of those dimensions at a time and doing all of the same stuff in those 3 dimensions and ignoring the others? Just taking any 3 of the available dimensions at a time?
Let's see, well, more or less like I did here, is that what you're saying? So yeah, so I did the 3 that I knew how to do first, and then I added one just with a simple rotation. You could probably iterate this procedure. You know, I suppose an inductive proof would let you write the volume element for n-1 dimensions, add one more direction. And
It's a little bit more involved than I thought, but yeah, I think I'm following.
but yeah, I would go with induction to do the general case, or I might just go to Wikipedia or Wolfram or someplace where somebody's already figured it out and laid it out. But yeah, I kind of like doing these things myself. It's fun sometimes. Okay, so now we know the total. I don't know if they're called steradians in extra dimensions, but the total angular integral over a 3-sphere. And now we can do our asymptotic integral so that for the upper limit, if we do IQP, all right, so we need 1 over 2 pi to the 4th. I'm only interested in the upper end of this up to lambda, but now we have dq over q, because there's an r cubed here, right? That's just going to be our magnitude q. And then we get the area of the sphere, which we just said is 2 pi squared, like that. And so we're going to get, well, let's see, there's a pi squared over 8, I guess, times log lambda. So that's, geez, log lambda. There we go. Okay, so that's our divergence, and then plus some finite part, which is in fact finite. So yeah, then the full matrix element is just going to be 3 copies of this. I've erased the full matrix element. It's just what we had. We're going to add together 3 of these. So we have an I of K1 plus K2, we have an I of P1 minus K1, and we have an I of P2 minus K1, all summed together times those factors we had in conservation of momentum. So this is one of the pathologies we're going to have to deal with. There are some others. So when we're dealing with
on that, before we go any farther, I
Yeah,
thought the other like integrals were part of different diagrams. So I'm confused as to why we're summing all 3 of them together for one diagram. Or are we just doing it for this?
no, each diagram is an additive.
And then we're just summing them all together.
Additive term in the path integral.
Okay, gotcha.
Right. Okay. The proof is from Wick's theorem. Remember that a product of any number of fields can be written as normal ordered terms times propagators, plus you come out at the end with a sum of products of propagators. So yeah, for just 2, you would have D1, D2 through 4 plus D1, 3, D2, 4. Remember, we did this one explicitly. 1, 4, D2, 3. This was a product of 4 fields. Plus other terms with normal ordered pieces. The vacuum expectation value of all the normal ordered pieces is 0. So your vacuum expectation value ends up being the sum of the diagrams corresponding to these 3 things. And those 3 diagrams correspond to various versions of these. So, so we draw all the diagrams corresponding to all those products of propagators, right? Different combinations of propagators, and we add them. And that's what gives that total vacuum expectation value. Okay. All right, so more pathologies. Yeah, tadpoles. So if we've got 4th order interactions, we can have something like this. Well, whatever order, that'd be cubic order with a 4th order interaction. Even at 1st order, you can have one of these guys. These are called tadpoles. And there's this clever thing you can do with these tadpoles. Sort of ugly. Let's do a tadpole and see what we get. Okay, so let's just do a single tadpole like that. So we've got x1, x2, and y here. So the integral we're interested in, we're going to have d for x1, d for x2, d for y. And then we're going to have an integral over momentum. I think I can call it just d for q. Yeah, so this one's not so bad. And we have an e to the I, p1, x1, x2, minus k1, x1. And then the propagators, e minus I, q1, then we're going to have, wait a minute, how many? 3 propagators, so there are three DQs here, sorry. D3, Q1, 4. D4, Q2, D4, Q3, 1 for each propagator. Then propagators, we're going to have an x2 minus y over q1 squared minus m squared times e to the minus I q2 dot, we have a y minus x1, and then that's over q2 squared minus m squared, and then we have e to the minus I q3 y minus y, because that's what this loop does, over q3 squared minus m squared. Okay, and then we integrate like crazy. Let's see, 3 propagators. There's 2 pi to the 4th, so I'll call it 2 pi to the 12th here. So we have a 1 over 2 pi to the 12th. Then 3 spatial integrals will give us 2 pi to the 12th. Okay, those go away. Then what? x1. We're going to get a del 4 of minus k1 plus q2. Then x2, we're going to have a p1 minus q1. And then y, I'll go ahead and do it. Okay, so this just goes away. So all we have is a del 4 of q1 minus q2. That's going to be our conservation of momentum. So then we still have the momentum integrals. So if we do 2 of those, and then denominators, right? q1 squared minus m squared, q2 squared minus m squared, q3 squared minus m squared. And then do a couple of the integrals. We're going to be left with d for q3 probably. But doing this one, we get a k1 squared minus m squared. Sorry, that's that's this one. Doing this one, we get a p1 squared minus m squared. I guess I don't need the 1 and 2 on there, but those are our usual canceling propagator things. And then we're left with a del 4 of p1 minus k1, conservation of momentum. And then the leftover integral is q3. Now, q3, what we have is, well, let's see, q3, L4, that's conservation. Yeah, it's just q3 squared minus m squared. So everything cancels except this last integral. I do believe I got it right. Yeah, there's an extra factor of I here. Yeah, each of these propagators has an I in it. So, you know, we're gonna have an IQ floating around. Two of those will cancel in the full matrix element. There's going to be an I squared there from the terms that cancel these extra factors. But the thing I want to look at is the leftover integral, which once again is divergent. And this time, well, we do a Wick rotation and a cutoff. So we're going to get the same volume element. And the only thing we have to worry about is the integral. I don't know why I'm making A's today, but the integral that diverges is going to have a q cubed d cubed q over q squared. And that diverges, sorry, it's q, you can do this exactly. It's q squared minus m squared here, like that. And that turns out to be, there's a lambda squared. I don't know, do you guys want to see the integral? It's in the notes. You can read it there. If you want to see it, I'll do it. It's short. You just do the numerator.
Sort of partial fraction decomposition thing.
Not that hard. You just end up with if you let z equal q squared, then this is just z dz times probably, that's not dq, 2 of those over z minus m squared probably becomes Euclidean. So z squared plus m squared. So it's just a z squared plus a log term. And then you put back let's see, this is, yeah, it's exactly that. You end up with a minus I over 16 pi squared. Yeah, I should give this for an exercise. This is not that hard. Let's see, except by then I've canceled the 2. So you come out with something like this. And that turns out to be z minus m squared times the log of z plus m squared. But this is with z equal to q squared. So this becomes lambda squared minus m squared log. It's this over, say, 0. We're going to 0. So 1 plus lambda squared over m squared is your final divergent factor. So you get both a logarithmic and a quadratic divergence here. And sorry, am I rushing through this too much? Do you guys want to see this, or is this good enough? I mean, it's integrals. You're okay. All right. So yeah, slow me down if I get trying to rush through. But I want to call this this whole thing minus
board
I.
check?
Sorry.
Board check.
Oh yeah. There you go. I want to call this leftover integral from the tadpoles minus I delta because each of these possible tadpoles is going to give a factor of minus I delta, and we can sum them all. So what happens here is we get a each time we add a tadpole. So we add another tadpole here. This is going to give us minus I delta. This one gives us minus I delta, where delta is this divergent thing, right? Then we're going to pick up a propagator here that looks like p squared minus m squared for a propagator on that line. And we get overall conservation of momentum. But in this way, you can do all of these things. So the total, the full series to arbitrary orders of tadpoles is, let's call it d hat, is we're going to get a, let me check here. So we get a plane propagator, dp, and then we get a sandwich with a minus I delta here with another propagator. And it keeps giving us things like this. If I'm, yeah. So in the next order, we get a propagator and a minus I delta and a propagator and a minus I delta and a propagator. And so on. Well, if I factor out, let's see, say the first or the last dp, then I can write the rest of this as 1 plus minus I delta times d plus minus I delta times d squared, and so on. And we know that infinite series, it's just 1 over 1 minus x. 1 over 1 plus x. I put a minus in.
Minus x is a minus.
Sorry, what?
It's 1 minus x, but our quantity is negative, so it becomes a plus.
Yeah, exactly. So I want to end up with a plus here, delta, and then dp. But now this this dp, if I put it in explicitly, this one's 1 over p squared minus m squared, and then we have I delta 1 plus over p squared minus m squared. Close bracket like that, and works good. So multiply through, and I get 1 over p squared. Am I writing this the right way? Yeah. P squared minus m squared plus I delta. Let me see. Is my sign? My sign's not what I thought it was. What's happening?
Yeah, you're missing an I in the propagator, so you get an I squared.
Oh, yeah. All right. Thank you. So then there's this I, which gives us a minus here. So I can put those two together like that. There we go. Yeah. Yes, the minus in the propagator. Good. So what happens is the net effect of all these tadpoles is a correction to the mass squared. Now, it's an infinite correction to the mass squared. And people are fond of taking these things in probably too much seriousness, but one imagines the bare mass and the renormalized mass. So the renormalized or measured mass. So what one says is that the net result, this sum, is the mass we actually measure in an experiment. And this mass differs from that measured mass by this quantity that happens to be infinite. So the picture is there's this, this divergent bare mass before you get quantum corrections. You do the quantum corrections and you end up with the measured masses, that total. Supported by renormalization theory, this is okay. You can probably take some careful limits. Like you could define m at delta and arrange m sub delta to be the difference between this and the measured thing, and take a limit, and that limit would converge to the measured thing because it's the measured thing at every level. There are more sophisticated ways to look at this, which, well, I'm not expert in. I'm not going to try to tell you about them, but people look at these things and worry about them and spent a half a century doing so. The bottom line is that quantum electrodynamics makes very high precision predictions that are correct. So I pose another exercise for you here. There's another diagram that I've called a Mandolin Diagram. So you can come in and at fourth order, you can split this way and build a diagram like this. So I invite you to compute the contribution of that diagram and see if you can iterate. I don't know if you can iterate. It may be hopelessly complicated, or it may be a similar thing to this, but give it a try, see what happens. See if you can sum an infinite series of mandolins. And as I say, I don't know if you can or not, but maybe it'll sum nicely. And at any rate, it's quick practice with these kinds of things. Oh my gosh, look at the time. How it has flown. But we have just time enough for me to write down some Feynman rules for scalar interactions. And they're in the notes. I suppose you guys are probably looking at the notes, but let's see if we can.
Professor, I don't know if you noticed, there's one error in the notes, just on this calculation we did, just the D, the D isn't canceled in the notes. There's an m squared plus delta times D. But
I see. In the very last step there, yeah.
Yeah.
I wondered what that was doing. Good, thank you. Yes.
There's also a factor of I.
Takes new eyes.
There's also a factor of I on the top. So.
There's an I. Yeah, okay. Yeah, this could stand to be cleaned up. All right. Thanks. Feynman rules for scalar fields. Okay, so the first thing, we always get conservation of momentum overall. And this is so we always have a factor of 2 pi to the 4th. We can always put that factor in if we want. The sum of the p out minus the sum of the k in. And yeah, it's handy to have various names for momenta, p and k and q. I'm constantly coming back to. And so what we're going to define is, all right, these are final momenta and this non-trivial scattering thing and our initial k's. We can write as this times I m initial to final, fi, yeah. And this is a definition of that m. So since we always get a conservation of momentum delta function, we extract it from the definition and just put it in as a rule. So now draw all connected diagrams. Then we're going to write the delta function. Then at each vertex, conservation of momentum at each vertex. So we're going to get a 2 pi to the 4th times del 4 at how did I write it here? Yeah, just the sum at the vertex of momentum. Okay, then a propagator for each internal line. And that's going to be I over 2 pi to the 4th. And then we have a p squared minus n squared with a complex offset technically. Okay, now I'm saying internal line here because the external lines all cancel, right? We've seen every time we get from the propagator for an external line, it always cancels those prefactors that we have in this matrix element. That's always the case. So let's not bother with the external lines at all. Then we integrate each undetermined momentum. This is the integrals over the q's. So, and each of those comes in with a E4q over 2 pi to the 4th. I'm wondering whether that 2 pi to the 4th is the same as this one up here. Is worth checking. Include minus I lambda over 4 factorial for each vertex.
Would that be capital N factorial? Is that the 4th order case? Or is that from the space?
4th order here. Yeah, so that would be n factorial for an n full, you know, phi to the n. Yeah, yeah, that's certainly true. Yeah, so we've done 3 factorial and 4 factorial, but these rules work. Now at kth order, include 1 over k factorial from the exponential at kth order. And finally, neglect external legs. They cancel. So, yeah, 2 minutes over, but there we go. So, and then I give a couple of, yeah, maybe more thought-provoking exercises. Draw, let's see, all connected third order diagrams for the phi-4 interaction. And I ask what happens at phi cubed at third order. Assume 2 in and 2 out for all of these. And then what else? Let's see.
I think that might be on a more updated version.
Oh, okay.
Right now it just jumps to QED. At least in the one
I stuck in a few exercises. I'll post these. So yeah, I ask you to draw some diagrams. I give you the QED interaction and draw a picture of what it looks like there, and ask you to draw. Let's see. What do I ask for? Yeah, second order diagram. Oh, and a 4th order diagram. Yeah, those are fun exercises. Those last 2 on the QED are simple.
Okay, never mind.
Yeah,
It is up on the newest one. Okay, I just re-downloaded it. It is on the newest one.
Oh, you're right. I did a little on this. So I'll post the current version. I have not yet, written much in the QED section. So, we're right up to the end of what I've actually written. So I'm going to write frantically between now and Wednesday. very similar rules hold for QED diagrams. There's some new stuff, but we might actually achieve our goal of doing a QED a QED calculation, some simple scattering, something for the final. So something to look forward to. In the meantime, I'm writing QED notes as quickly as I can. So I'll stick around for questions, but we're out of time.
Hey, yeah, I guess maybe I'm being silly, but so the 4 factorial comes from the order of the interaction that we put into the Klein-Gordon field?
Yeah, that's right. If you've got 5/4, you've got 4 lines leaving, and all right, there are 4 choices for which field goes out this line, 3 for the next. So that always cancels by the time you add up all the possible ways that those 4 fields could connect.
Okay.
And that's
that
why you put it in the interaction in the first place.
Yeah, it's a constant, so it's artificial, but it's normalization.
Yeah, that's
okay.
right. That's right. Yeah, you choose your interaction carefully, and you can avoid some stuff. My nose is very red. Meg and I went biking yesterday, so my bike helmet covered the top part, but I forgot to put on sunscreen on my nose.
You're a bit of a Rudolph.
Yeah. It's not drink, it's sun, really.
Yeah, that's what they all say.
Yeah, right. Okay. So how's it going, Alex?
It's going well, I think.
Good.
Yeah, I owe you a lot of problems, but I'll get in there, I swear.
Well, yeah. So do that.
When do you want our problems due for this class? Are you going to give us till the 5th, or
no?
Do you want to miss?
No, I'm going to give you up until the time I start to write up the grades, which is probably, well, I don't know. When is the final technically?
The last day. For this class, I don't know. The last day of the finals is May 5th, I know. So I don't know when.
Yeah, I know. But yeah, let me see.
I don't even know how to check that, I guess.
I'll have it in just a sec here.
Sure.
Yeah. Exams. I just had this open this morning, actually. Hello. That's wrong year. Wait a minute. I got last year's. All right, here we go. Let's see, final examination schedule 2021. Summer, spring 2021. Final examination schedule. Let's just see. So yeah, when is this? This is noon. Let's see, Tuesday, Thursday. What are we? We're noon. Yeah, probably scheduled for Monday, May 3rd, 11:30 a.m. Monday, Wednesday, Friday, or Monday or Wednesday or Friday. That's probably the one we're falling under. Yeah. Now I don't want to put it off until the 5th. So it looks to me like we could justify Monday.
Okay, that's fine. Yeah, that's fine. Yeah. Yep.
Yeah, I'm not. Yeah, let's see. This is where 12 or 12:30 common finals not otherwise scheduled. Nothing exactly applies to us, actually. It's sort of weird.
Right.
Yeah, I don't know if we're in a proper 11:30 slot or an improper noon slot, but I'm going to go with Monday.
Okay.
So, yeah. So anything I get up to that point, at that point, I'm going to, check what people have turned in and, assign grades. If you want to get them in earlier, that's not a problem.
Yeah.
These things, you can't always just knock them out. Let's see. Yeah. I forget how long the QED problems take. And I'm not sure what we'll be able to cover by then. But seems to me I remember them taking, multiple days to work out a problem. So don't push it right to the end, because some of these things are longer.
Okay.
I think the ones we've done so far have been pretty quick, but it's not always the case. So, but let's see, you're getting it? It's yeah.
I think it's fine.
You could go off and do a scalar field, like, whip off those exercises. Do those exercises now. Get used to it a bit.
Yeah, I think the problem is I still owe you in the Dirac. I think I'm still in the Dirac chapter that I owe problems for. Is that?
Mhm.
I don't know how far behind. Is everybody kind of? Am I pretty far behind relative?
Yes, you're pretty far behind. I'm not sure how far behind everybody else is, but
Yeah, that's fine.
that's no way to judge.
Yeah, no. And I know one of the hang-up was I got most of the way through the Dirac problems, but then there was that one, the new way to do that.
To find the basis vectors,
Yeah,
the Lorentz boost.
for whatever reason, I was having trouble with that one, but I know it's pretty straightforward. I don't know why it was coming out weird.
Yeah,
But-
it's the first part's easy. The second part's a nightmare. All right. So okay. I gave you the matrix, right?
Yeah.
I've enhanced the stuff back in the earlier chapter where we talk about Lorentz transformations. And so you've got this little matrix of a 2x2 matrix of 2x2s. That's, just identities and dot sigma type stuff, right? And you can whack that on a unit spinner, and basically the unit spinners are just going to pull out the columns, right? So that part's easy.
That's what I thought, but I kept not getting it. So and I got demoralized and then COVID.
So the trick is writing that in terms of the energy and momentum, because you've got sinh and cosh of half angles, and the connection between the usual, like, velocity, energy, momentum, V over C, beta is tanh of phi.
Mhm.
But you have half angles. You've got sinh and cosh of phi over 2. So it's in that conversion that you just have to keep your head, right? And also look at the answer, because when I finally got it, it surprised me that what I was looking at actually was the right thing. But the fact that you're looking at something like E plus M things actually makes it work.
Mhm.
There's a common M factor to everything, and that drops out. And it was a little surprising, but it actually does work. But you're going to mess with the hyperbolic functions a bit.
But yeah, you are supposed to just take the basic, the unit spinners, right? One
Yeah.
1 0
Yeah,
0
so
0.
1 0 0 0 is going to pull out the first column of the transformation matrix, and that's the right answer, right? That's it. But writing that in terms of ENP and seeing that it is in fact the same thing that we wrote the other way, writing it in terms of ENP, you've got to fuss with hyperbolic functions a bit. Double angle formula is half angle.
The basic way is to get that transformation you gave us and multiply it in with the metric, the metric and the gamma I, whatever the other, whatever component you're looking at, right?
Yeah.
We had like lambda, because we're doing this transform, and we usually have the h times gamma to the I, whatever component you're looking at for the spinner. Is that right?
Right, to do a vector, right? Now, okay, am I thinking of the right problem? Because
I think you are, and I might be just being stupid.
never noticed you doing that.
It's right above 6.3 in the April 13th notes. So page 157 is what I have.
Okay, almost there. This is getting big.
That's a great book. We're getting there.
Thanks. I'm having fun right now. Okay, yeah. So there's
Thank you.
that's lambda. Yeah, that's it. You've got all these half angles where psi there is the rapidity, and
Mhm.
tanh of psi gives you the velocity ratios. So, you know, mv gamma is the yeah, let's see, I think it works out. Cosh psi is the usual gamma factor, 1/1 minus beta squared. But what did I ask you to do? Did I ask you to find a vector or a spinner form? I asked you to find the basic spinners, right?
Mhm.
So where's
Oh.
the problem I invited you to solve? Let me find the exercise.
Yeah, you're
Oh,
supposed to.
it's back where we were finding those basis spinners, right?
Mhm. And then it looks like boost. The idea was to boost the spinner solutions. And
Yeah.
talk about it. It was back in one of the earlier chapters where you drew the problem out. Let me see if I can find it. Oh,
Let's see. Okay, so yeah, basis identities. All right, we're getting there.
yeah, 255 was kind of the equation I was following though then.
255. But yeah, I'm looking for the actual problem you're trying to solve.
That was
Let's
on page
see.
157. I'm sorry.
Oh, okay, 157. All right. Okay.
I'm sorry.
Yeah. All right. There's 157. Oh, yeah. Okay. All right. Got it.
Well, so
And
am I
then,
just being
okay, and then
stupid?
255. All right. So, yeah. So I want you to get the form for the spinners, right? Not for a vector. A vector involves h in the gammas, right? So you take psi bar, h, gamma, psi, and you got to work all that out quadratically, and that will give you the boost equation, right? That will give you the usual thing. But what I'm asking you to do on page 157 is to dot 0 1 0 0 0 0 1 0, those unit vectors into that matrix. That's going to pull out the 4 columns of the matrix.
Yeah.
And then I want you to show that those 4 spinners are the same as the ones we derived by solving the equation 6.11, 6.12, in a general frame.
Okay, I was getting myself confused because I kept thinking that 255, like I kept thinking we were supposed to get the space vector, and so I was trying to use 255 to get the.
Oh, yeah.
Then,
right below 255 is V. It's the inner product of psi with gamma psi. Yeah, I've written it out there. Right below 2.55 is the vector transformation.
Yes, and so I think I was trying to do the vector transformation, and that.
Well, that's good for you.
Okay. But that would just give you a Lorentz contraction. I mean, that would just be a Lorentz boost, right?
Yeah. This is a boost.
This is just a Lorentz.
Yeah, that's a general boost in the n hat direction.
That's the type of stuff I was getting out, was like gamma factors. And I was confused why I was getting gammas. Okay.
Yeah. So if you compute the V that's written right below 2.55, you will find the normal boost equation. Take n to be in the x direction, and you get x is x minus vt gamma, right? The usual thing. And that's definitely a problem worth doing. I should have given that as an assignment somewhere, but it's really nice to see that works out. And for that formula, you're bringing in lambda twice, and you get double angle formulas all over, and it works out to be just in terms of the rapidity. So your normal boost stuff just falls right out. But for the spinners, you have to dig deeper into those half angle things to to get those normalized basis spinners. it was a little tricky. You know, I
Okay.
was going along thinking it was going to be all afternoon, and then it suddenly worked, you know, and I was very pleased.
I mean, I'm very pleased because those 3 matrices were not fun to multiply. That it wasn't very fun to
Oh,
keep my
no,
algebra in
no,
order
not-
to do the boost
non-trivial,
case.
non-trivial. Although, you know, one of the important factors is that n dot sigma squares to 1.
Yeah, it
That's
was
handy.
working, but it was still like,
Yeah, it gets a little long.
yeah.
Yeah, I think I forget which class it was now. I worked out the rotations that way. Did I do that in quantum? I might have done that in quantum.
Which way? Sorry, pardon me.
Oh, in the quantum mechanics class, at least in one of these classes, I've worked out like a general rotation to show that doing it with spinors really gives the same formula as doing it with 3 real rotation matrices.
Both maybe even, or maybe it's in the gauge notes. But was that? I feel like that was almost in here too. But maybe it was.
Maybe I'd put it in here. I forget. Yeah, rotations and let's see. Yeah, I don't know. You know, and it may be more than one place actually. But it's nice to see that you really can do that and get. Yeah, I don't remember where I did this. Yeah, maybe I did give this as a problem. So yeah, here's this general form for SU2. You know, any time spent with SU2 is time well spent.
Yeah, yeah. For these same reasons, because I kept seeing 4 vectors and just saying, oh, it's a 4 vector. I kept seeing 4 entry vectors and saying, oh, that's what part of the stupidness. But no, it's 2 2s.
Yeah, you got to be careful with spinors in 4 dimensions are by a curious fluke 4-dimensional, but it's a complex 4 space. It's different.
Yeah.
It's a totally different space. Let me see. Now, I don't know. I wonder if I put this in the quantum notes. Let's see if I have those open here.
I mean, I know we were doing like the rotation generators and stuff earlier in the QFT book too.
Yeah. Yeah, somewhere oh yeah, here we go. Looks like translations. Plus G, no. Symmetries. Well, I don't know where I did this. You know, I keep doing it. It probably is in the gauge theory book too. Let's see. Where's gauge?
There's a lot in there. It's a good guess, but it's in there.
Yeah, I put a whole mess of stuff in there.
And we didn't have a big problem like do the Dirac field then, quantize the Dirac field all on our own.
Quantize the Dirac field. Oh, let's see. I don't think so. I think I asked you to do something with the E and M.
Okay. I think I'm done with. I did all of chapter 6, but that problem. So I think I'm at least in chapter 7 now, for what that's worth.
Oh, okay. It's definitely in the gauge theory book.
That's where I read it.
3-dimensional rotations done 2 ways, one with SO3 and one with SU2. And I show explicitly, X prime is this combination of X's, and it's, you choose your vectors to be the axis in 2 directions perpendicular, and you can see it's a rotation around those perpendicular directions. And yeah, maybe in quantum, I just referred to the gauge theory pages or something, or for you guys in field theory. I don't know.
Yeah, I did those problems for what it's worth though. So I think there is a problem on get that form out.
Okay, all right. So then what? Where's the quantum field theory book? yeah, this really need a way to jump to any place. Gosh, I can't believe I've used up all our field 3 notes. I've got to write some more quick. Yeah, you know, I got hung up because I was thinking, oh, you know, I should teach a BRST quantization.
Yeah.
And no, I shouldn't. You know, we can do that over the summer, but I should just choose an easy route to getting out QED stuff, so we can, you know, move on with, you know, a cross section or something. Anyway,
It's all fun for us. So
yeah,
all good for us,
I'm enjoying this. This is really fun. You know, pulling this all together and, you know, digging through my books. I might have to sneak into my office one of these days and pull out a couple more books.
I did have a actually material question too on the lecture today. That on the tadpole proof that we're doing just at the end, it seemed like in the text even, and I don't know if this what you wanted to take this out, but it seems like it was worked out with a Y2 vertex. And I was wondering if that was there's like a section right before you use the same Y for the little loop. I was wondering if the tadpole is like can be regarded as a limit of a third order diagram. And I guess I was wondering how limits work. And so like if we had a third order diet where it was like a line and then a half arc limit.
So yeah, that's interesting. Yeah, you could do that. Okay.
It almost
try it. So yeah, so okay, so what did we have for the cubic? Because we did that diagram, right? Or did we?
We did do the,
let's say cubic, second order cubic. Yeah, but we didn't do. Oh, okay. We were only looking at 2 particles in and 2 out. So if we, here, let's have a look. You see here. So yeah, so you know, we did these diagrams for second order cubic like that. But yeah, you could have a second order cubic like this with 2 in and 2 out. Or let's just ignore that and do this one. So what you're saying is take the limit as these 2 approach, right?
You get a tadpole.
And then you get a tadpole, 4th order. Well, I like it. That's a great problem. I'll put it as an exercise. But yeah, I'll try it and see what happens. Yeah, that would be interesting to see, because, you know, I mean, we're building, you know, complicated things out of simple things here. You know, we're really describing something that's much more complicated than any of this, right? And you know, building it up by little pictures that we can say words about as if that's what was happening, but it's not. Yeah, the most illuminating thing I've seen about that was, you know, somebody talking about Fourier series, you know, and you know, you've got you know, that waveform, and you write that as a Fourier series and say, well, you know, at lowest order, it's this sine wave, you know. No, you know, you've got to go, you know, 1,000 terms in Fourier series before it really starts to look like that. Maybe not, but I mean, Fourier series converge pretty quickly. But you know, it is not that. It's that, and you know, these Feynman diagrams are a way we have of getting something close to that.
Yeah, and I guess that would maybe be the more interesting way. Maybe that's the question. Like because this picture was almost, we had like a 3rd order approximation to a 4th order diagram because we had the separation.
Yeah.
Is there a reason, like, you can say just generically above an nth order that the corrections will be smaller than this? Because like, oh, the higher order diagrams are roughly like this shape, like
No, in fact, it gets worse. It gets worse and worse at higher orders. So in fact, what we're dealing with are the asymptotic series. These there's actually, I think, the closest approach to the correct answer, and then Feynman diagrams diverge. They don't uniformly converge to the right answer.
That's, I guess, what I'm asking. Dang. Wait, so
Yeah,
there's like there's an optimal truncation point?
Yeah, and I don't know where it is, but the problem is that the number of diagrams goes up something like n to the n. And, so where you may be converging because of a small interaction constant, you're diverging faster because of the large number of diagrams. So at some order, you're going to be, just adding in too much infinite stuff or something. Boy, what's this weather? The wind's picking up again.
Fascinating. That is so cool. It's gross is what it is. Ew. So bad.
Yeah. Oh, it really blows up here.
Yeah, you guys are up on the hills, eh?
Uh-huh. Yeah. Yeah. And
It'll be nice in a couple months. That's what you
well,
want.
actually, it's supposed to be getting warmer. I mean, it may snow tomorrow, but it's supposed to get warmer through the week. We went bicycling yesterday. We went down and saw the ducks. And we like to bike into Logan. Over on 4th West, the ducks always accumulate in the canal there. And
oh, cute.
we saw a few. They're not out in force yet, but you'll see 20 ducks hanging out in somebody's yard. But it doesn't look like we'll have another ride for a few days. Maybe later in the week it'll be warm again. But
my
springtime.
My neighbor has a couple ducks that he feeds that come to our house, and my cat just loves them. She thinks they're so neat.
Yeah. Uh-huh.
They're so cute.
Yeah. Great. Okay.
Right. Yeah. Well, I'm gonna try to play catch up, but I'm doing my my grant renewal paper this week. So, but I should be fine. If I think I'll have plenty of time. If you give us till the Monday, that's great.
Yeah. Yeah. Don't put it off too far.
Nope. I'll start on it when I get bored with this.
Fit in some exercises for breaks or something, and make some headway.
Yeah, and I'll send you an email if I have any questions. Like I just did.
Okay, great. All right.
Thank you so much, Professor.
You bet. See you, Alex.
Have a nice day. Bye bye.
You too.